Welcome, dynamics students. This mini lecture will include a demo problem for rigid bodies, planar motion, kinetics. So we'll be again looking at relating forces and net moments to the rotational acceleration of a rigid body that is in planar motion. So that acceleration is going to be in one direction, k hat, because we're going to be moving in the xy, and then we will relate net forces in our remaining orthogonal directions, x and y, I hat, j hat, to motion of the center of mass of that body. And in this case, we are looking at a diving board. So we have a spring diving board, kind of a competition board here, and it is at the moment of interest very much in the horizontal position, and it is supported by a hinge at one point attached to the ground, and also by a spring about midway through. And there's a diver just jumped off of it. So we're told that the diver just jumped off. And so this is point A is at the hinge, and the spring is halfway down the board. Board's 1.5 meters. Halfway and another 1.5 meters. So it's 3 meters total length. And the spring has a spring constant of K equals 7 kilonewtons per meter. So we can, if we know how compressed the spring is, we've got a spring force at the time. So the mass of the diving board, M board, we're told, is 25 kilograms. So we're in metric, we don't have to deal with any slugs. And someone wants to know AX and AY at the moment that somebody just jumped off the end of the board. So they kind of deflected the board a little and they jumped off of it, and the board is going to maybe spring up a little bit. Pins maybe going to have to hold it down. Spring is going to be pushing back up. So let's see if we can. So that's why we're being asked for the acceleration. We're going to need to know the acceleration of the board. We want to know what's reacting at this pin just at the instant in time that this person jumps off. What else do we know? Board's uniform. Density equals same everywhere. So that tells us where the center of mass is. So XCM is right there. So that'll be probably useful for later on. At the instant that the diver jumps off, I'm reading this out of the book here, and I'll give you a text reference. The spring is compressed 200 meters, or excuse me, 200 millimeters. So that's easier to say. 0.2 meters equals delta L spring. So between that and the spring constant, we have a force being applied right underneath the center of mass of all places at the moment of interest. And the board's not rotating right at that instant. So it's at rest right then. Not going to stay at rest, but it's at rest right at that instant, and it's horizontal. So these two, the orientation is important. We'll use that in our FBD, and we'll use this in our kinematics to get an expression for angular acceleration and relate that to the acceleration of the center of mass, and then we'll try to use that in our FBDs to say something about these two support reactions. So before I go any further, I'll give you a reference. This problem was drawn from the Hibbler 14th edition dynamics book, and it is problem 1781. So if you want to take a look at it and follow along, feel free. It's got a little bit nicer figure, but we've got all of the essentials. So let's use a coordinate system. I'm going to use my favorite coordinate system, which includes I hat positive to the right and j hat positive upwards. J hat. Need to give myself a little bit more room there. See if I can put my hat over my unit vector j, and positive alpha is going to be in the counterclockwise direction, which we may end up having in this case. We'll see. So next task after that is our FBD, and I'm going to FBD the board, the rigid body that is going to accelerate. I guess I could FBD the spring, but I'd probably wouldn't do me as much good saying something about the board. Okay, so the first thing I'm going to do here is identify this as my center of mass, so I can remember it for the kinematics. And I have a spring force acting upward because I've compressed the spring, and I know that that's equal to the spring compression at that point in time, that is the time of interest, times the spring constant, which is 7 times 10 to the third newtons per meter. So that is a number I have. The diver jumped off the board. He or she just jumped off, so there's no mass, so there's no diver weight on the end of the board. They're gone now. I know that the board is aligned in the I hat direction. That's also going to be important. Let's see, the board does weigh something. It doesn't weigh much, but it does weigh something. And I know where the center of mass is, so I know that the board weight of 25 kilograms times gravity is going to be, I can assume that it's working right through the center of mass, and then I'm going to have an AY and an AX. So I'm going to draw them in, I'm going to draw AX in the negative I hat direction. We'll see what it ends up being. Okay, so now I'm going to use what I have on my FBD to write some Newton's second law expressions. So I'm going to sum the forces in the x direction, which is all of negative AX is going to be equal to the board's mass, which is 25 kilograms, times acceleration of the center of mass in the x direction, whatever that ends up being. Sum of the forces in the y, we're going to have spring force pushing up minus the weight pushing down plus AY is going to equal mass, kilograms. Let's erase that and draw it a little neater there. Newton's second law, MA, and this time it is acceleration of the center of mass in the y direction. Now I have a moment expression that I can look at, and I am, again, as I did in our previous problem in this little mini lecture set, I'm going to take the moment about point A in this case. So I'm going to end up needing to get a moment of inertia for a rod about its end. So I can say the sum of the moments about point A equal IA times alpha. And I've got, because if I take the sum of the moments about point A, I eliminate AY, I can get a number for this and then match it up to, I can calculate IA based on what I know about a uniform rod being rotated at its end, and then I can solve directly for alpha. So that's one of the things I need to know, and it is also key with a little kinematics applied to getting my center of mass acceleration in the two vector directions. So let's take a look at that. So let's tally up our moments. So we've got, basically we have a negative moment coming from the weight. So we're going to have a negative 25 kilograms times gravity. And that's acting at 1.5 meters. Plus the spring force, this, which ends up being 1,400 newtons, significantly bigger. And that's also acting at 1.5 meters. So they're both acting right against the same point. So now I need a value for alpha. So if we look up in our tables, we can find alpha for a rod being rotated about its end. We're going to have m times the length of the rod squared divided by 3. So this will give us 25 kilograms times total rod length. That's why we needed that extra 1.5 meters, by the way. Even though we didn't have a force acting at the end, we needed to know how long the rod was to calculate its moment of inertia. So 3 meters squared divided by 3, and so that all gives us 75 kilogram meters squared. So we now have what we need. This value for I sub A, we have a number in terms of this force sum, which allows us to solve for alpha. So we'll just, I won't crank through the algebra. I've already done that in my notes, but I can use that to say that alpha is going to be equal to 23.1. Let's write that a little neater. 23.1 radians per second squared. Okay, and it's a positive number, so not surprisingly it's going to start trying to rotate like that. Okay, so once again we now have an angular acceleration, and we now need to use some kinematics, our horizontal orientation, and our zero angular velocity. And I'll go to red here, and so I'm going to basically say, all right, I got a rigid body, I got one point, and I got another point, and I've got an angular acceleration. So I can say AO, whoops, I meant A is an acceleration, not A is in point A. The acceleration, I want one point versus the other point. The acceleration of point O, which just so happens to be the acceleration of the center of mass, so that diving board, is equal to the acceleration of point A plus alpha cross R from A to O minus omega squared RAO. That's 0, initial conditions. That's 0 because it's a fixed pivot, real convenient. So the acceleration of our center of mass is going to be equal to alpha, which I got a number for, and we'll just say this is, we'll remind ourselves that's in the k-hat direction, since we need to calculate a cross product, crossed into RAO, which we know what that is. That's 1.5 meters in the I-hat direction. So we're going to end up with a k-hat cross I-hat, cross I-hat. So our A center of mass is only going to have a component in the j-hat direction, because in this case our RAO only had component in one direction. So as it turns out, the board doesn't have to exert any force in the horizontal, because that ends up being 0. So that made the statics a little easier. In this case, we had no force in the horizontal direction because we had no acceleration. So no force needed to be applied. The board wasn't trying to move that way. So acceleration of the center of mass ends up having a magnitude of 34.65 meters per second squared, and it's going up. So if we feed that back in here, we have a spring force, we have a weight, we can solve for a y algebraically, and we end up with an AY of 289 newtons, and it ends up having to be downward in order to, even though our acceleration of the center mass is upward, we've got a very large number here, so we end up needing to add a little more to balance that out. So, but again, it's just back feeding in and using the algebra. So key steps. Again, coordinate system. That's keeping all of our sign conventions straight. Definitely important when we start dropping in the kinematics. Our conditions that we needed to solve for forces, and understand those initial conditions that were essential for our kinematics. Knowing what we needed, what are we looking for? Well, we could just go calculate everything we can say about it, but which is fun, but we might have other things to do. We needed to know something about springs to get our spring force, and our orientation and initial conditions. FBD, just like statics. Newton's second law, not just like statics. So some of the forces and some of the moments are going to be equal to the mass of the body times the acceleration of the center of mass of that body in each orthogonal direction. Some of the moments is going to equal the moment of inertia times for the given point about which we're taking the moments times our angular acceleration, and then kinetics as needed to give us our additional expressions to solve for what we need to solve for. And again, as you saw, we had two, basically. We could say that we should say ACM y, and that's all in the j. We ended up with an ACM x equals 0. We had two equations coming out of our kinematics expression. So that's it for this mini lecture and this quick problem. We'll have one more demo problem with rigid body planar kinetics. You'll see much of the same steps. These are fairly simple problems. Obviously, we can add more forces. We can have much more complicated motion. You'll see that with some generalized motion. So far, these have been what's called fixed rotation. Everything's been rotating about a fixed pivot. We've always had some point where we could say acceleration was 0 because it was a fixed pivot. Even if every point is moving translationally, and we have both translational and rotational motion at every point in the body, it doesn't matter. We'll just add one more line in our expression for our kinematics, and we can still solve for these. So we'll see that in future problems. So, but that is it for this problem and this mini lecture.